The global transition to offshore wind and subsea power transmission is colliding with a fundamental material limit. High-voltage direct current projects require specialized insulation to withstand extreme dielectric stress. By 2026, global demand for extra high-voltage grade cross-linked polyethylene will reach 235 kilotons, far exceeding the projected global capacity of 145 kilotons. This structural deficit emerged in 2022 when demand first outpaced manufacturing capacity. Consequently, lead times for subsea cables have expanded from 15 months to 60 months. Grid operators can no longer secure timely delivery of critical transmission assets. The supply of this critical polymer is highly consolidated. Two chemical conglomerates, Dow Chemical and Borealis, control 86% of global capacity. This extreme concentration leaves the entire global offshore wind pipeline vulnerable to localized industrial disruptions. Entering this market requires massive capital and highly specialized technology. Production requires cleanroom polymerization and advanced multi-stage filtration systems to eliminate microscopic impurities. A single contaminant particle larger than 70 microns can destroy a subsea cable. Engineering trends are compounding this material bottleneck. To reduce transmission losses, operators are shifting from low-voltage lines to 525 kilovolt systems. This transition increases the required insulation mass by over 200%, demanding 1,900 metric tons of polymer per 100 kilometers. At these higher voltages, dielectric stress reaches 20 kilovolts per millimeter. Any microscopic defect triggers electrical treeing, causing catastrophic subsea failure. This physical constraint mirrors the 19th century reliance on gutta percha, proving that modern high-tech grids remain bound to obscure, single-source materials. Landlocked mineral assets in the Central African Copper-Belt face severe logistical friction. Exporting copper and cobalt via legacy road networks to southern and eastern ports requires journeys of up to 2,600 kilometers. These routes suffer from chronic border delays and deteriorating infrastructure, inflating transit times to over 30 days. The western-backed Libido rail corridor bypasses these bottlenecks by establishing a direct 1,300-kilometer link to the Atlantic. This rail connection reduces transit times to just 30 to 36 hours. Logistics costs will fall by over 50% to approximately $140 per metric ton. This infrastructure corridor represents a calculated geopolitical intervention. The United States and the European Union have committed over $1 billion to modernize the line and fund a 1,200-kilometer extension into Zambia. This capital directly challenges Chinese dominance over Central African mineral logistics. By 2030, the corridor is projected to transport 1.2 million metric tons of copper and 120,000 metric tons of cobalt annually. Securing this direct Atlantic route insulates Western supply chains from geopolitical choke points. It structurally realigns the flow of battery-grade materials toward Western processing hubs. Pressurized water reactors constitute the backbone of Western nuclear power. These systems require highly specialized chemistry to prevent internal corrosion. Specifically, they rely on high-purity lithium-7 hydroxide as a primary coolant stabilizer. The global supply chain for this isotope is highly consolidated. Rosatom controls 10,500 kilograms of annual enrichment capacity, representing 70% of the global commercial supply. The United States operates 65 pressurized water reactors, but possesses zero domestic commercial enrichment capacity. American reliance on foreign isotopic separation has created a critical vulnerability. By 2026, total United States fleet demand will reach 10,000 kilograms annually. With domestic commercial production remaining at zero, the import dependency gap is absolute. To sustain operations, utilities rely on dwindling federal stockpiles and direct imports from geopolitical rivals. A single reactor requires up to 200 kilograms of lithium-7 annually. Any supply disruption would immediately threaten the operational continuity of the domestic nuclear grid. This bottleneck is governed by rigid physical laws. Reactor coolant requires an isotopic purity of at least 99.9% lithium-7. Lower-grade lithium contains lithium-6, which absorbs neutrons to produce radioactive tritium. Reducing purity to 99.00% increases tritium production 100-fold, violating environmental limits. It also accelerates primary loop corrosion by 500%. This structural dependency mirrors the early Cold War reliance on single-source Congolese uranium, exposing a fragile node in modern energy security. High-performance computing clusters require a structural transition from copper to optical interconnects to sustain parallel processing. Modern artificial intelligence training networks rely on 800 gigabit and 1.6 terabit optical transceivers to maintain low-latency data transfer. The physical foundation of this optical layer is highly consolidated. A single Japanese firm, Sumitomo Electric, controls 53% of the global indium phosphide substrate market. Together with AXD Incorporated, this duopoly controls nearly 3/4 of the global supply chain. Synthesizing single-crystal indium phosphide is governed by severe thermodynamic constraints. At its melting point of 1062 degrees Celsius, phosphorus exhibits an extreme dissociation pressure of 27.5 bar. To prevent the volatile phosphorus from escaping, manufacturers must use high-pressure inert gas and liquid boric oxide encapsulants. This volatile environment induces thermal stress, keeping 6-inch wafer yields below 50%. Consequently, a single 6-inch wafer costs over $1,200 to manufacture, which is nearly 8 times the cost of an equivalent silicon substrate. Mismatch between artificial intelligence infrastructure demands and material processing limits is widening. By 2026, global demand for high-speed transceivers will reach 16 million units. This requires 440,000 6-inch equivalent wafers, but global supply will reach only 165,000. This 62.5% deficit forces transceiver manufacturers to operate at suboptimal capacity. Lead times for optical interconnects now exceed 12 months, directly delaying the commissioning of next-generation computing clusters. The structural integrity of modern civil infrastructure relies on hot-dip galvanizing to protect steel from atmospheric corrosion. This process consumes 60% of global zinc production. While raw zinc mining is geographically diverse, the secondary smelting step is highly consolidated and energy-intensive. Smelting requires up to 4,000 kilowatt-hours of electricity per metric ton of refined metal. Consequently, severe decoupling has emerged between mine supply and refined metal output. By 2025, global refined zinc production is projected to contract to 13,350 kilotons. This contraction occurs despite stable global mine output of 12,410 kilotons. The resulting refined metal deficit will widen to 150 kilotons, marking the 5th consecutive year of supply shortfalls. This structural deficit is driven directly by regional energy crises. High electricity prices in Europe have forced the indefinite closure of major smelting assets, including Neostar's Butyl facility and Glencore's Nordernam plant. These closures have removed 410 kilotons of annual smelting capacity from Western markets. The loss of local processing capacity has triggered a surge in physical delivery premiums. Rotterdam physical premiums remain elevated at $430 per metric ton, a 258% increase over 2020 baselines. United States Midwest premiums have tracked this rise, reaching $470 per metric ton. Domestic steel galvanizers must compete for a dwindling pool of non-European refined metal imports. The geography of global zinc refining reveals a critical geopolitical vulnerability. China controls 47.5% of global refined zinc smelting capacity, processing 6.5 million metric tons annually. In contrast, North America holds just 7.5% of global capacity. The combined capacity of Europe and North America is insufficient to meet Western infrastructure demand. This structural deficit forces a heavy reliance on Asian refined metal to support domestic utility-scale solar installations and grid transmission line buildouts. This bottleneck mirrors the late 19th century aluminum industry, where abundant raw ore was rendered useless by a lack of localized, economic smelting capacity. Advanced semiconductor fabrication requires ultrapure water of extreme chemical purity. Global demand for this critical input is projected to reach 315 million gallons per day by 2026. This rapid expansion is outstripping the chemical industry's capacity to deliver specialized purification media. Consequently, lead times for custom-engineered ion exchange vessels have quadrupled to 24 months. This delay exceeds the critical 18-month threshold for fab construction schedules. The divergence introduces structural delays of up to 12 months in stabilizing new water purification loops. The bottleneck is driven by the physics of advanced lithography. Transitioning from legacy 28-nanometer to advanced 3 nanometer nodes increases water consumption per wafer by 216.7%. Complex three-dimensional transistor architectures require aggressive, multi-stage rinsing steps. To maintain ionic purity below 1 part per trillion, resin volume requirements scale nonlinearly. A 3 nanometer process requires 5,800 liters of resin per 10,000 wafer starts. Furthermore, these resins degrade rapidly, requiring complete replacement every 12 to 18 months to prevent organic fouling. This critical purification step relies on an exceptionally consolidated supply chain. 3 chemical conglomerates control over 90% of the global market. This extreme concentration presents a systemic single point of failure for global semiconductor manufacturing. High barriers to entry protect this oligopoly. Producing monodisperse polymer beads with 0 microcracks requires proprietary emulsion polymerization. Qualifying alternative suppliers requires up to 36 months of continuous testing to prevent catastrophic wafer yield loss. This dependency mirrors the early 20th century chemical industry's reliance on specialized platinum-rhodium catalyst gauzes. Just as that single node constrained global fertilizer production in 1913, modern silicon fabrication remains tethered to a fragile chemical triad. The front end of the nuclear fuel cycle is constrained by a highly consolidated chemical processing sequence. Before mined uranium can be enriched, it must undergo conversion from uranium trioxide to uranium tetrafluoride. This hazardous step requires specialized, corrosion-resistant fluorination reactors. Decades of underinvestment have left Western conversion infrastructure severely depleted. By 2028, Western reactor demand will reach 20,500 metric tons of uranium equivalent. However, domestic operational capacity is projected to reach only 16,000 metric tons. This leaves a persistent annual deficit of 4,500 metric tons. Historically, this structural gap was balanced by Russian exports. Rosatom maintains a stable conversion capacity of 20,000 metric tons, controlling 40% of global throughput. This single-source dependency leaves Western utilities highly vulnerable to geopolitical supply disruptions. Western conversion capacity is concentrated in just 4 facilities. Nameplate capacities are highly misleading due to operational and chemical constraints. In 2026, the combined operational output of these facilities will fall short of the 19,800 metric tons required by Western reactors. Orano's French facilities represent the largest Western asset, but are limited to 12,500 metric tons due to reagent supply constraints. In the United States, the restarted Metropolis plant is restricted to 5,500 metric tons. Legacy equipment issues also limit the United Kingdom's Springfields facility to just 25% of its capacity. These physical bottlenecks prevent Western utilities from decoupling from Russian supply chains. While raw uranium is abundant in Canada and Australia, the West lacks the chemical infrastructure to process it. This structural deficit mirrors the early 20th century German monopoly on coal tar intermediates, which paralyzed Allied die and explosives manufacturing. Physical scarcity of conversion capacity has triggered an unprecedented price shock. Between 2018 and 2025, spot conversion prices escalated by 465%. Prices surged from $11.50 to $68 per kilogram of uranium. Long-term contract prices followed this upward trajectory, rising to $58 by 2026. This sharp divergence began in 2022. Following the geopolitical rupture in Ukraine, utilities scrambled to secure non-Russian capacity, turning a low-margin service into a premium-priced bottleneck. This economic reality confirms that energy security is governed by chemical processing limits rather than raw resource availability. Until the West builds redundant, high-capacity fluorination reactors, its nuclear fleet remains tethered to Russian state enterprises. The transition to energy independence is blocked not by capital, but by the hard physics of chemical synthesis. Northern Australian critical mineral assets are fundamentally constrained by land distance. Trucking heavy mineral concentrates thousands of kilometers south to Adelaide or west to Fremantle imposes a severe economic and environmental penalty. This overland friction renders many world-class deposits economically marginal. Routing exports through the Port of Darwin reduces overland haulage by up to 75%. It also cuts maritime transit times to East Asian refining hubs from 16 days to just 8. This logistical realignment secures a direct, low-carbon corridor for non-Chinese material processing. Unlocking this mineral reserve requires targeted capital deployment. A $1.5 billion Australian dollar expansion of the Port of Darwin is currently underway. This funding scales bulk export capacity from 3.2 million metric tons to 12.8 million metric tons by 2028. The infrastructure is engineered specifically for high-purity materials. Dedicated dry bulk terminals prevent cross-contamination between lithium and rare earth concentrates. This specialized design ensures that upstream chemical purity is maintained through the export gate. This logistics corridor directly alters global supply dynamics. By 2030, combined critical mineral exports through Darwin will exceed 1 million metric tons annually. Lithium concentrate will comprise the bulk of this volume, reaching 850 kilotons. Crucially, the corridor will export 95 kilotons of rare earth oxides annually. This provides Western defense and industrial supply chains with a secure, non-Chinese source of magnet feedstocks. This infrastructure push mirrors the late 19th century development of the port of Duluth on Lake Superior. Just as Duluth unlocked the Mesabi Range to fuel American steel, Darwin bypasses legacy bottlenecks to secure the primary inputs of the modern energy economy.